what I was going to ask. I think it was pretty similar to problems that you've had on the homework recently. All right. You know, just in terms of the way things are set up. And I need to get, there we go, slideshow. Here we go. All right. It's pretty similar to the way the recent homeworks have been going. So it's a lot of Fourier stuff. It's all Fourier stuff. All right. Homeworks 7 and 8. The other thing that I would expect is something maybe similar to what you had on problem 4 of the last exam, okay, which was also Fourier related. So go back and look at that one too, because that's a pretty similar one to what you might see as well. I mean, it's all related. It's all Fourier series, Fourier transform related. So it's all, it all kind of fits in there. Okay. This is one here that is like the practice. I think it's like problem 3 on the practice exam, where I basically, it's kind of the opposite of what I gave you on the homework. What I've done is I've given you the Fourier transform, and I'm asking you to tell me what is x of t. All right, so what is x of t? So I've told you the Fourier transform. On the homework, it was the other way around. I gave you x of t, and you had to tell me the Fourier transform. So if I gave you this problem, how do we start?
First, you'd probably want to find the period.
Yeah, you could find the period or the fundamental frequency, right? So what's the fundamental frequency of this guy look like it's going to be?
10 to me.
10. Yep. So omega naught equals 10. And if I look at this, you know, at the end of the day, I'm going to want to get this x of t in probably in the, you know, I think in the homework or in the practice exam, I tell you that I want to have it in the form, I write it like this, alpha naught. And you guys aren't going to like the way I wrote it.
Wait, why is the fundamental 10? Wouldn't the period be?
Fundamental frequency is 10, right?
Oh.
Remember, this is my omega here. So this is 10 radians per second. So my fundamental period would be 2 pi over
yes.
10, right?
Yes, I see it now.
Yeah. All right. So let's say I want to get it in that form. So my x of t should look like what I wrote there at the bottom of the slide. Okay. And I wrote alpha naught. Alpha naught is the DC term. Alpha naught is C naught over 2 and A naught over 2. I just find that over 2 thing to be kind of annoying. All right. So I know what the fundamental period is, but these impulses basically tell me the amplitudes, I guess, in the complex form of the series. Okay. So what I want to do is I want to start by building this guy up in terms of the alpha n e to the j and omega naught t, like that. Okay. So my suggestion is probably to do this frequency by frequency. All right. So what frequency do I want to start with here? What frequency do you want to start with? That's a better question. I know what I want to start with.
Start with the DC frequency?
Yeah, I'm going to start with the DC frequency. All right. So what is the DC term of x of t going to be?
2.
Almost.
4 or?
4.
Nope.
1. I'm just guessing.
You're right. It's 2. I mean, 2 is the magnitude of it, but it has an angle.
Oh, no, 2e to the j 0 or 2.
So remember the way this guy looks is I've got 2 plots here, right? I got a plot of the magnitude and I got a plot of the angle. Okay. At omega equal to 0, it says that term, so I could think of it as I have 2 e to the j 0t. All right. That's that guy. What about this negative 180 angle? That means that it's actually the alpha 0 term, right, is 2e to the negative j 180 degrees. What does that equal to?
So it would be -2?
-2. So in other words, it's -2. I can't express that the DC value in terms of the magnitude. I can't express the value as -2. I have to express it as 2 with an angle, right? So the DC term of this guy is -2. Okay, so I'm going to write it over here. So I'm going to say x of t is -2. All right, for now, that's the first part of it. What do I do? What would be the next frequency that I would look at here? Omega equal to what?
10 and minus 10.
10 and minus 10. And I put those two together. Right? So how would I construct those into a signal here? So help me out with that. So for omega equal to 10, I'm going to have something that is e to the j 10t plus something times e to the negative j 10t.
E to the 60, e to the j60.
Yeah. So what would I put? What would I put in front of these guys?
3.
3. All right. But I need to take into account the angle, right?
Yeah, e to the j 60.
E to the j 60. All right. And then what about for the negative 10 term?
It's 3e to the negative j 60.
Negative j 60. Like that. Okay. If I combine those into a cosine, what do I get?
Don't you get like 3 cosine?
Not
3 halves.
3 halves, you're right. 3 halves cosine.
So when I'm looking at the exponential always has half of the amplitude. So that would mean the amplitude would be 6.
6. So 6 cosine 10t
6
Plus-
cosine 10t
plus 60 degrees.
plus 60 degrees. Yep. Okay. So that means that this is plus 6 cosine 10t plus 60 degrees. Okay. And again, I'm just using Euler's identity there. Remember, Euler is always, if I have a cosine theta, it's a over 2 e to the j theta plus a over 2 e to the minus j theta. Okay. All right, that's what I use to do this step here. Okay. All right. What do I do next?
Move to the next frequency.
Okay. What's the next one? 30 and negative
30 and
Yep, 30 and negative 30. Okay. Well, what would I have for that? So I'd have an e to the j 30t term. And I'd have an e to the negative j 30t term. All right. What would be what goes in front of the e to the j 30t term?
1.
Yeah, 1. That's right. 1.
E j to the 30.
E to the j
Minus
negative.
30.
Negative 30, yeah.
Yeah, negative 30. Okay. And then what about the other guy?
30?
Yep, so it'd be 1 e to the j 30 degrees, okay? Which if I combined those is going to be what?
2 cosine 30t plus 30.
2 cosine 30t minus 30 degrees. Minus 30 degrees.
Why was the top one plus 60?
Well, because if you look at the one here, right? If I so this is the e to the j 10t term right here, right? So if I combine those, so in other words, problem is I'm probably skipping steps and that may be confusing. This guy is the same as 3 e to the j 10t plus 60 degrees plus 3 e to the negative j 10t plus 60 degrees. If you look at that, that compares more cleanly to that Euler's identity, right?
Yeah, that makes sense.
Where my theta is 10t plus 60. Right? That's the same thing that I did here. All right. Questions about what I did there? Okay.
Why does it, hang on, can you go back? Why does the -30, for the -30, it says -30 degrees and then 30 degrees, but then for the positive, it says 30, then -30
So
degrees.
this is the frequency label here. So this is, so the number written at the top of these impulses is the angle. It's the number that's being represented there. Whereas these values here, maybe I should have written them differently, are meant to demarcate the frequency location.
Well, like the -30 has, like, there are 2 degrees for the 30. That's why I was confused for that.
Well, so for the, if it's just, okay, I see where you're going.
Yeah.
So
I'm looking at the negative part of the graph. Angle.
yeah, for the negative part of the graph, I have 30 degrees for that one. So it's, if you notice, they're always opposite of each other. So this one, yeah, 10 radians per second, it's 60. So at -10, it's -60. Here at 30, it's -30 degrees. So at -30, it's the opposite of that.
Okay.
So,
Yeah.
so easy way to see this is, don't skip steps like I did. All right. I'm taking advantage of the fact that I'm more comfortable with this, right? So if I look at this, I can do it the same way I did the previous one, right? So let's just combine these two terms into one, right? So that becomes e to the j 30t minus 30 degrees plus e to the minus j 30t plus or minus 30 degrees, sorry. So it better be the case that these guys have theta and negative theta when I combine them. And they do, right?
Yeah.
If you multiply those out, that's exactly what's going to happen.
Okay.
You follow that?
Yeah, I do. I was just looking at the graph all wonky.
Yeah, I mean, so when you look at the graph, I mean, just, the simplest thing to do is probably to do it in 2 steps like this. Okay, well, so if I see something at 30, then I write that down and it has an angle of -30. If I see so he needs to get paired with the guy at -30, and that guy has a little degree symbol on him, doesn't he?
That's what it was also throwing
That's
me
probably
off.
that may be what's throwing you off there.
Yeah, that's what it was.
Yeah, okay. All right, so this was +2 cosine 30t minus 30 degrees, okay? And then I have one more term to include here, right? What's the other term I need to include?
40 and -40.
40 and -40, all right? So the magnitudes of those guys are both 2, okay? So I'm gonna do that guy over here. So I'm gonna say 2 e to the j 90t, and then there's gonna be a term 2 e to the negative j 90t. Okay.
40.
Sorry, 40t. I just failed. You guys want to grade my exam and fail me, I'm sure.
No, just so we clear this up, that would only be minus,
used to it after a while.
1. So,
That's, I like the way you grade. Yeah. Okay, so how would I, how do I take into account the angles there?
E to the j 90.
And okay, e to the j 90 goes on which term? The 40 radians per second or the -40?
It'd go on the 40 because that's where it's located.
Yep, so e to the j 90. And then this would be e to the negative j 90. And if I want to do this slowly, I can say that's 2 e to the j 40t plus 90 plus 2 e to the j 40t, the minus sign in front, plus 90.
So when the signs agree, it's going to be a positive, and when they disagree, at least for the phase.
Just write it out the way. I mean, don't try to find any tricks. Just write out the graphs, as they come, and then try to combine them like this, right? And then I should see I've got a theta and a minus theta, right? So this guy has basically become 2 e to the j theta plus 2 e to the minus j theta, where my theta is equal to 40t plus 90 degrees, like that. Follow that?
Yep.
Okay. So what's that make the total here? If I sum those up, it's going to be a cosine, right? What's the amplitude of it?
Oh, 4, be 4 cosine 40t plus 90.
Yep, 4 cosine 40t plus 90. So that is the total signal.
And for the exam, is that as far as you want us to go?
So I think if you look at the practice exam, practice exam is set up probably similar to the way I would set up the exam. So if back in the exam, I probably would have another step. Let me see. I have it open. So if you look at the way I set this up, so I ask you to do it in this form. I probably would ask you to do it in the complex exponential form, and then ask you to do it in the cosine form, and then I also ask you to do it in the cosine sine form.
Okay.
Now I don't know if I would ask you to do that all of that on an exam or not, but I sort of did that just as a means of forcing you guys to make sure that you also understand and remember how to do those conversions.
Yeah, so it's a matter of just converting in between everything.
Yeah, that's right.
Okay, cool.
Because there were a lot of problems with this conversion between these series on exam 2. All right, and so making sure how to do those conversions is something that definitely will reappear in some form on this exam. All right. So
when you're converting between those two forms, would you just be able to like mine it? Because you know that sine is like the 90 degrees. So could you just do that to convert, or would you have to convert that differently?
So the conversion, if I have it in this form, I've got formulas that I gave you guys for that. But the other way to do it is to just say, all right, well, I can use a trig identity here. And I can look that up and basically see that if I've got cosine of x plus y, that becomes cosine x cosine y minus sine x sine y. That's all that I basically did, right? And then if you look at that carefully, well, what's x going to be? Well, x is going to be 10t, right? So this will
And
be
y will be 60 degrees.
Yeah, and so these guys will be numbers, right? Just a number. Whereas these are functions. This is an f of t, right? This is a g of t. And then these will be coefficients, right? This will be a1, and this will be, so the b1 here is going to be negative this. So it's going to be negative b1. I think the negative sign is part of what is messing people up on that as well. But those are just going to be numbers when you do that. A lot of people did that right, but I noticed some confusion with that on the exam. All right. Any last questions on that?
Well, the question that because you said it was a DC frequency. Is it always going to be that, or like
What do you mean?
Because I think you asked like the first question you asked what frequency that was.
Mm-hmm. Yeah, so I mean, I don't always have a DC term, but in this case I do, right? If I have a term at omega equal to 0, that means that there's a term in my signal that's DC.
Okay.
What if the angle was 0 instead of negative 180 on the DC term? What if it wasn't?
So if it was 0 degrees, then the number would just be 2.
Okay.
Right? So what angles could I have for the DC term? There's really only 2 possibilities, right?
0 and 180.
0 and 180. Yeah. I can't have a 45-degree DC term. if I had 2e to the j40, why? So 2e to the j45 is my DC term. It doesn't make any sense because I can't have a phasor for a DC term, right? That doesn't make any sense. I can have a positive value or a negative value. Those are the only two things you can have as real numbers. The thing to remember, and this goes back to even some of the things I saw in exam 2, in the real world, there's never anything imaginary, right? And so I'm always so if I have e to the j something t as my answer for something, most likely I'm wrong. Because if I had a system and I put a cosine voltage into it, I'm going to get a cosine voltage out of it. It might be shifted, might be scaled, but I'm not going to ever get a complex output. So, you know, the only thing I could ever get is a DC, the only thing I could ever get is a positive or negative value, right? And if I have a 180 or negative 180, then that just means that I have a negative 2 volts. If otherwise, the only option would be 0 degrees, right? But I couldn't have anything other than that because it would imply that I had a imaginary DC part, which doesn't make any sense. All right. Questions? Okay. All right. Silence.
I actually follow this a lot better than before.
Yeah, it clicked. I like it.
Okay. Yeah, I'm glad we did an example. All right. So let's jump into what we talked about last time was I kind of tried to motivate this idea of, you know, where we would kind of apply this. So if I had a signal, and let's say as an example, let's say I was trying to drive a motor with an Arduino, so a microcontroller of some kind. This is a pretty common thing to do. It's a DC motor, and the question I asked you last time is, what kind of voltage do I give a DC motor? Well, ideally a DC voltage. But creating a variable DC voltage is very hard to do. And if I'm trying to control the speed of the motor, I need a variable DC voltage. And so commonly what we'll do is we'll say, okay, well, let's apply a voltage that looks like this guy here. So he's a square wave of some kind, which means if he's a square wave, he's periodic. And if he's periodic, he can be represented as what?
As a sum of cosine or sine waves.
Yep, that's right. And so basically that means that I'm putting into this DC motor a bunch of cosine and sine waves. And the thing I showed you last time, I showed you a video basically to say, well, if the frequency of this wave was really low, meaning if the period was really big and the frequency was really low, what you saw was that you would see the motor spin during the time that this voltage was high, and the motor would stop spinning when the voltage was low, and then it would alternate back and forth. But if I made the frequency higher and higher, you just saw a smooth motion from it. So let me ask you this. If the motor just gives a smooth motion, what's happening?
It's gradual.
It's like a low pass filter.
Basically, yeah. So you're using that term, yeah, low pass filter. Basically what's happening is all of those sines and cosines are getting removed or filtered out by the motor. And it's only responding to the DC term, okay? So, you know, basically what you say is this guy can be thought of as a voltage that has an average value, whatever the A naught value is, plus all these other, you know, cosines, right, that are there, right? N omega naught T plus theta N, all the other stuff. Somehow I have set this thing up and I've set the frequency high enough that all this stuff goes away. All right, and somehow it doesn't affect the speed of the motor. And so what we said is there's a way to think about this in terms of what we call a transfer function. So I apply a voltage and I get a speed out. All right, and this thing called a transfer function relates those things. So you're actually familiar with the idea of transfer functions from 2112. Right, where you've been learning about it in the context of AC circuits. But the real way of doing this is actually what impedance analysis is. Impedance analysis gives you a transfer function. impedance analysis is basically a Fourier transform. All right, it's related to all of this stuff. So in general, if I have any kind of a circuit or the general thing I refer to as a system, right? This guy's not really a circuit because what I have is a circuit that's applying a voltage to some electromechanical thing. The output is speed, the input is a voltage. That's an electromechanical system. It's more than a circuit in that particular case. So sometimes I use this term system. But all the analysis, all the tools that you talked about in 61 or in 2111, 2112, and here apply, whether I'm talking about electrical system, mechanical system, whatever I'm talking about, I can still apply those. All right. So let's just try to understand that again. So we said, let's say I have a differential equation that looks like this. And let me simplify it down. And let me just say I have A1 dV dt plus A0 v of t equals Vs of t. And so let's say my Vs of t is a cosine like this. How do I represent this thing? We don't write it as a cosine omega t plus phi, but we've said, how do we represent that guy? Not that way, but as what?
Are you talking about Euler's?
Well, Euler's identity is one way to write it, right? So I could write this in terms of Euler's. The other way I can say this guy is what? He's the real part of what? What would that be the real part of?
E to the j omega t.
Well, I'll just write, I'll go slow here, right? It's a e to the j theta, where theta is what? This is what a lot of people got wrong.
Omega t plus phi?
Yeah, omega t plus phi. Right? So it's the real part of that. And so I end up with saying it's the real part of a e to the j phi e to the j omega t. All right? And so what we do is we say, okay, well, let's apply this as the input. And then at the end, take the real part of that result. Okay? So we said, all right, I basically plug in here a e to the j phi e to the j omega t. All right. If I do that, I know that at the end I have to take the real part of the result. Okay. What do I do for my output? So v of t. What do I guess for v of t if that's the case?
I mean, wouldn't you want just a to the j phi?
Well, basic idea, real part of what? Not a in this case. It's going to be a different amplitude, right? So let me call it b. And what would I write next to that guy? Just to remind ourselves, it should be b cosine omega t plus some angle. So we'll call this guy, I don't know, I'll call it phi b, okay? Like that. So if that's the case, how would I write this? How would I write it in complex form? Real part of b times what?
Times e to the j. Well, I mean omega t. Well, yeah.
Yep. Yeah. So I'm just breaking them up there. So e to the j omega t times e to the j phi b. So what we did is we said, all right, well, that means I guess this, and then I drop it into here, right? So I guess that and I drop it into here. And I just do the analysis on the complex part, and at the end, I remember that I have to take the real part of it, okay? That was the thing a lot of people didn't do right on exam 2. So I got to remember to take the real part of that at the end. So that means I got A1 d by dt of b e to the j phi e to the j, so phi b omega t, plus A0 times b e to the j phi b e to the j omega t. And that's all equal to this guy here, a e to the j phi e to the j omega t. Now, what is true about both sides of that equation?
e to the j phi, or ej omega t, sorry.
ej omega t, right? So this guy, when I take the derivative of this term right here, the only thing that depends on time is what? Just this e to the j omega t, right? This guy basically becomes j omega a1 plus a naught. And then I'm going to factor out here b e to the j phi b ends up on both sides. And this would be equal to a e to the j phi. All right, so the e to the j omega t terms go away. Okay? And so when I look at this for a second, what I see here is a e to the j phi, b e to the j phi b. Those things are things that you call those the phasors in 2112. So in 2112, you would say, well, my input is, if it's a cosine omega t, so let's say it was 5 cosine 10t plus 30 degrees. You would say that the phasor for that thing is 5 angle 30 degrees or 5 e to the j 30 degrees. That's the phasor that represents those things. That phasor is, if we look back to like this example that we did here at the beginning, these guys here, these alpha n's, are the Fourier transform terms, right? And so if I look carefully at this, what that kind of tells me is these guys here, this is the Fourier transform at the frequency omega. And so I look at this and I say, well, from that previous slide, I had A1 times j omega plus A naught times B e to the j phi b was A e to the j phi. So this guy here is, it looks like, what I would call, and this guy here, these are the Fourier transforms of those waveforms at those frequencies. And so what it says is I can rearrange this whole thing if I wanted to. And I could call this guy, I'm gonna write it like this. I'm gonna bring this, shift it around and say V of omega over Vs of omega, which is simply A e to the j phi B e to the j phi b is equal to 1 over j omega a1 plus a naught. Now so the reason I write it like this, what this says is basically you did the same thing, or you've done the same thing in 2112, where you basically did this using phasor impedance analysis. But essentially what it says is if I can relate the Fourier transforms of the inputs and the outputs to each other, and they're related to each other through what we call the transfer function. And that transfer function is something that you can generate using impedance analysis, but it in general comes directly from the differential equation. Okay, so let's say I had this guy right here, right? So V in of t is my input, V out of t is my output. So if that's the case, what's the differential equation that relates those things? How would I write the differential equation in this case?
With KVL?
Yeah, KVL, right? So I'd go through and do my KVL, and you would see that this guy becomes RC dV out by dt plus V out equals V in. Okay, like that. All right. Now, you guys learned how to write basically using impedance analysis, right? So you guys, how would you have related, if you used impedance analysis, what would you do? How would you use impedance analysis? Based on what you know from 2112.
Sir, to phasor domain?
You convert to the phasor domain, all right? And you would say, well, I got a phasor input over here for V in, and I want to find the phasor for V out. What's the implicit assumption when you're doing an impedance analysis? What's the implicit assumption about all the signals? What kind of signals are they? What do the waveforms look like? They're what?
All sine waves.
They're all sine waves. Okay. So that analysis really actually comes out of the Fourier transform analysis. And this is useful because not all systems are circuits. Some systems are electromechanical, and maybe what I have is a relationship that's just a differential equation like this. So what this says is if I have a differential equation like this, I can convert this guy into a transfer function from the differential equation straight away. Anytime I have a d by dt, I replace that with what? So if you looked at what I had here, right, or what I started with, every time I have a d by dt, what happens to that term when I have a sine wave like this? Right, so a d by dt, like this guy, what does the d by dt always do? When I take the d by dt of e to the j omega t, what do I get?
You just basically pull the j omega out front.
Yep. So I always end up with this. Let's say I took the second derivative, so d squared by dt squared of e to the j omega t. What would I get then?
You would get negative omega squared e j omega t.
Yeah, you took it one step further than I would. I would take the j omega down twice. So I'd get j omega squared, right, times e to the j omega t. So basically, I always have e to the j omega t going in, right? This is the input. And my output is always just j omega time to whatever order derivative I'm taking times e to the j omega t. All right. So what that says is if I have something like this and I wanted to get to the transfer function, what would I do? If I have d by dt here.
Oh, hey, sorry about that. I was looking online. I work for Griffith and Adams. We're we're just looking for some like
Someone's off mute.
aerial services.
So yeah, they're unmuted.
Yeah, can you guys?
School over.
Somebody needs to mute yourself out there.
We're in the site preparation phase currently.
I don't think he knows.
I was wondering, like, what?
I believe it's.
What do y'all typically charge?
Yeah, I think it's Ivan.
Or no, it's Ivan. You're right.
Yeah, you can mute him, Dr. Cox.
Where do I do
Never
that?
done anything like this before.
You guys know?
If you click on participants at the bottom, you should have an option.
Yeah.
I think he might have just figured it out.
No, he's still unmuted.
All right, well, he's disappeared.
Oh, he figured.
Yeah.
He's muted now.
Okay.
All right. Well, here's where we are. All right. If I've got this guy here, all right. If my inputs are sine waves, what do I do with that d by dt? What do I do with that derivative?
You make your guess.
Well, I mean, so I can make my guess, right? I can go through that whole process, but this says there's actually sort of a simpler way to even do this, right? If I'm just interested in the steady state piece of this, anytime I've got a derivative, I could just say that if I jump this over to the what I call the frequency domain, what you guys have called the phasor domain, if I jump this over to what I call the frequency domain, so in other words, it's in the frequency domain, things are a function of frequency, okay? So they're a function of frequency, not a function of time. So technically the thing that I'm saying here is instead of thinking this as V in of t and V out of t, I think of this as V in of omega and V out of omega. Okay. So if that's the case, what it says is I can make a relationship, a function that relates these two things together. You guys have done that with impedance, but where does that impedance come from? Well, it comes from the Fourier transform, right? So if I jump to the frequency domain, I'm assuming that my inputs have that form, in this case, be a e to the j phi e to the j omega t, okay? If that's the case, if I have that d by dt, what do I replace that d by dt with if I plugged something of this form into that equation? what always happens with the d by dt, the first derivative?
J omega comes down.
J omega comes down. So this guy becomes j omega RC plus 1 times whatever my V out phasor is, right? So really whatever the Fourier transform is at that frequency is what I get here. So this V out of j omega would be, it's an amplitude, right? And it's a phase angle. Okay, this guy is the value at that particular frequency. Okay, and so this becomes, on this side, it's whatever I have here at the same frequency. So the thing is that the phasors that you've been doing all this time in 2112, what they were basically the Fourier transform at that particular frequency. All right, if you think about it, what you have when you have a phasor is you have an amplitude and an angle. That's exactly what those alpha values are. Those alpha values that we looked at back here are an amplitude and an angle at each of those frequencies, right? So the phasor really just was a Fourier transform. It's a more formal way of looking at it like this. And so this gets me to, if I write this as V out of omega over V in of omega, I usually write it like this, and I call it the transfer function. It relates the input to the output, all right? And so in this case, it would be 1 over j omega RC plus 1, all right? And I can write this a couple of different ways. I can also write this as V out of omega is equal to V in of omega, so V in of omega times h of omega. So these are all basically 3 equivalent ways of writing the same thing. All right. You guys follow that? We need to look at an example to see how to follow that. But it's go ahead.
Oh, I was going to say, yeah, that makes sense.
Okay. This, we learned this basic idea of I can get the transfer function looking straight away at a differential equation. I could get it if I have a circuit, always from doing impedance analysis, but I don't always have a circuit. I might have an electromechanical system of some kind, in which case, I've got a different problem I got to look at. So if I'm looking at something like what I showed here, the output is speed, but the input is a voltage. One's a mechanical thing, and the other is an electrical thing, right? So I got a multi-domain problem that I have to solve. All right, so I got to find a way to relate those concepts a little bit. All right, so in general, what we say is it's a lot easier to do analysis in the quote frequency domain. And you know that because you've been doing that all this semester in 2112, all right, rather than looking at the differential equation straight away. Now, what this sort of says is I've got a way of looking at things from what I think of as the systems viewpoint. All right, so if I have I think of my system, so this guy could be a model for an RC circuit. All right, so I could have an RC circuit where my output is V out, my input is some voltage source. In general, I call my inputs X of t, and I call my output Y of t. Now, the frequency domain is not something I can see. The time domain is something I can see. In other words, you stick your hand in a wall socket. We've talked about that before, right? You stick your hand in a wall socket, you will feel pulsations in time, not in frequency, in time. In other words, you'll feel a pulsation repeating, but you don't see things in the frequency domain. If you look at a voltage coming out of a function generator on an oscilloscope, you see it in the time domain. In other words, the things that happen in the real world happen in the time domain. The frequency domain is basically we transfer things over to the frequency domain to be able to think about them. All right, so like what I was talking about last time, I think I showed the radio example last time, where I can say, well, the signal that's received on the radio is this ugly looking thing. It's got a whole bunch of sine waves in it, but I can look at it in the frequency domain using the Fourier transform, and I can make a lot more sense of what that signal is when I look at it that way. Okay. All right. So I've got this basic picture that we draw with a block diagram where I say, okay, I have my input, and I basically say I put that input into some system which is represented by a transfer function, and then I can figure out what the output is. And so using this whole idea of everything really that we've talked about up through now is basically different ways of talking about the same thing. If my input is ultimately a sine wave, I can represent it using the complex exponential, and then the output is another complex exponential with the same frequency, but I multiply the output by whatever the transfer function is, so whatever's in this box. So if you look at how does x of t and y of t relate, how do they relate? If you look at here's x of t, here's y of t, how do I relate those things?
Frequency.
What's that?
Well,
what did I do to y of t, or what did I do to x of t to get my y of t here? I multiplied it by h of omega, right? So look at this. I took x of t is equal to a e to the crap there. So I took that times h of omega is my y of t. All right, so it says if I know what the transfer function is, what I need to do is I need to multiply x of t by h of omega, and I get my y of t. All right, and so it says if I put a sine wave in or a complex exponential in, because these guys are basically the same thing. I can always think of a sine wave as complex exponentials. Then I'm going to get a sine wave out, and its amplitude is always going to be the amplitude of the input times the magnitude of the transfer function at the input frequency. And the phase of the output, or the angle of the output, is the angle of the input plus the angle of the transfer function at that frequency. All right, this is something we've been doing all along, but this is a more formal way to kind of think about it, because we think about it usually in terms of transfer functions. The reason we think about it like this oftentimes is because usually when I'm designing a system, and you'll see this in the project, when I'm designing a system, I think of designing the h of omega first. So if I want to have a circuit that is a filter, then I typically design h of omega, and then I think of what the circuit could be based on what that h of omega was. So you guys are used to, from an analysis perspective, so in 2112, Yahoo gives you a circuit, you do the impedance analysis, you say what the transfer function is. Designers don't do that. Designers say, here's the transfer function, give me a circuit that gives that transfer function. So design is the opposite of what you're used to, right? And so we learn this kind of mathematical approach because it's easier to do design from the mathematical approach and then get to a circuit, as opposed to go from a circuit to a function, all right? So what this always sort of says is, if I know the Fourier transform of the input, I can figure out the Fourier transform of the output very simply. So at a given frequency, if I know the Fourier transform at a given frequency is this, then the output is basically going to be just simply that, that magnitude of my input times the magnitude of the transfer function, and then the angles of the transfer function and the input are just going to add to each other. All right. So this basically emerges down to a single process. All right. And we're going to do an example here in a second. Basically says, if I know what my input is, I take its Fourier transform. Then I figure out what the transfer function is, from looking at the differential equation. And then I figure out, using the transfer function and the Fourier transform of the input, I figure out what the Fourier transform of the output is, and then I inverse transform it. Now, this is actually the exact same process that you would use in 2112, except you haven't been calling it that. Instead of calling it the Fourier transform, you say, well, I figure out the phasor of my input. All right, and then I do impedance analysis to get a transfer function. And then I figure out the phasor for the output, and then I inverse transform. Those phasors are what we call the Fourier transform, all right? And ultimately it allows me to get a lot more general and start talking about, well, what happens if I have something other than a sine wave coming in? I can actually begin to do some more robust analysis with it, okay? So let's take a look at an example. So I've got this RC circuit here, and I want to go through these steps, okay? So this is good practice. The first step here is at least good practice for the exam. Okay, so step one, I want to get the Fourier transform of the input. So in this case, Vn of t is my input. All right, so let's write out here what this should look like. What would the Fourier transform of this guy be? And let's write it out two different ways. Let's start out with just a picture. I gave myself 2 slides for this. I did. All right, so let's do it this way. Vn of omega, magnitude, in angle. Okay. All right. So first of all, how do I do this? How do I figure that out? How do I figure out the Fourier transform of that guy?
So it is the Euler's identity on the cosine and the sine function, right?
Yep, I would do Euler's identity on the cosine and sine function. Now what about the 5 there?
So that would just be a magnitude of 5 with an angle of, and the angle just goes straight up, so 90.
0.
An angle of 0, right? So 5 is equal to 5 e to the j 0 degrees. Now, what you just said, Andrew, is if I had, remember we're plotting this, so we're saying what I have here, my Fourier transform is a complex function of frequency. And I can only plot, when I'm plotting versus frequency like this, I can only plot magnitude and phase, or real part and imaginary part. If I was plotting in the complex plane, I'd be plotting a vector, right? So if I was plotting something that was straight up in the complex plane, that would be, you know, J5, right? Or 5 with an angle of 90 degrees. In this case, if I'm basically saying, all right, I'm plotting the magnitude and the angle separately. So for the DC term here, I've got a magnitude of 5 and an angle of 0. So there's nothing there. Okay. Any questions about the DC term before I move on?
When do we divide by 2 for the DC term?
This is, so when we do this, right, I'm basically thinking of this guy in the form like that, okay? If the over 2 comes in if you do one of the other forms of the series.
Okay, just not the exponential form.
Yeah. And the way that I think about this is, if I'm in the exponential form, I think of it like this: half of the energy exists at the positive frequency and half of the energy exists at the negative frequency. So just right off the bat, right? So at 2 pi 60, there's a term, right? So at 2 pi 60, what's the magnitude going to be at 2 pi 60 and at 2 pi negative 60?
4.
Not 4. Remember, we do this in terms of the complex form of the series, right? So we say Vn of omega, the Fourier transform, is the sum over all the frequencies that apply here. So alpha n, how did I write it over here? Alpha n, this guy's a function of frequency. Okay. Equal to minus infinity to infinity, like that. All right. So let's just write this guy as a Fourier series first, and then we can map it to the alpha n, or map it to the right frequencies, right? So looking at this guy here, let's take this more slowly for a second. All right. Taking this more slowly, just writing it out as a Fourier series, what frequencies are present in this particular signal?
60 and 80.
60 and
180.
180, right? I'm going to give myself a little bit more space here. All right, write this out a little bit more slowly. Okay. All right, so looking at this, I've got 60 and 180 hertz. What other frequency do I have?
0.
0. All right. So, Doesn't want to change on the fly. There we go. All right, so I had x of t equals 5 plus 4 cosine 2 pi 60t, and he had an angle to him, right? Plus 60 degrees.
Plus 60.
Yeah. All right, and then there's another term, which we'll get to that other term in a minute, all right? All right, now, if I want to write this as a Fourier series, this guy is my DC term, my alpha 0 term, okay? What is the fundamental frequency of this guy?
60.
60. All right, 60 hertz. All right, so I'll write it this way. F naught is 60 hertz. Omega naught is what?
2 pi 60.
2 pi 60. Okay, so what n values do I have here? So I'll do it this way. N, F, omega. What n values do I have? I have n equal to 0. What frequency is that?
0.
0. Okay, I have n equal to 1. What frequency is that?
60.
60. And 2 pi 60 is my omega. What about 2? Do I have a second harmonic?
No.
No. All right, so that frequency would be, I mean, I guess technically I'll say it's 120 and 2 pi 120, but I don't have any terms there. And then my third harmonic I do have. So I have a 0, a 1, don't have a 2, but I do have a 3. This guy is 180 and 2 pi 180. Okay, so looking at that, that says to me right now that when I define this series, I'm going to have an alpha 0 and what else? An alpha 1 and an alpha minus 1.
And you can have a B.
Let's stay complex.
Okay.
All right, I'm going to have an alpha 0, an alpha 1, alpha minus 1. What else am I going to have?
Alpha 3 and alpha negative 3.
Alpha 3 and alpha negative 3. Always get your series in this form, in the complex form. And then you can easily go back and forth between whatever other forms you want to do. But let's get it in the complex form, because that's really the one that we use the most. Okay? All right, looking at this guy. So I know that I can get it into, those are the only non-zero alpha values that I should have. Okay? So let's make sure we can figure out what alpha 1 and alpha minus 1 are, right? So this guy right here is going to become what? This guy's going to give me my alpha 1 and my alpha negative 1, but help me do it. How do I write that guy in terms of complex exponentials?
Well, wouldn't it be 2e to the 2 pi 60t?
All right, let me do it this way. 4 over 2, and I'll do it slow. 4e to the j theta plus 4 over 2 e to the minus j theta, where my theta is 2 pi 60t plus 60 degrees, which if you then plug that in, you're going to get 4 over 2 e to the j 60 degrees times e to the j 60t, or 2 pi 60t. Okay, plus 4 over 2 e to the minus j 60 degrees times e to the minus j 2 pi 60t. Now, where's my alpha 1? Where's my alpha minus 1?
Well,
First
yeah.
half.
Here, alpha 1 is the first half.
That's alpha 1. That's
your
alpha minus 1. Okay, like that. So when I look at this and you say, well, how do I know about which one is a DC term that's twice or whatever? The way I look at this is whenever I'm using the complex form, I always have half the amplitude, always. That's why I usually write 4 over 2, rather than simplifying it out, I usually write it that way, just so in my mind I know that I divided by 2. So the way I think about this is in the complex form of the series, there's always 2 frequencies that give me that cosine. One is a vector, right? This is a vector here, e to the j 2 pi 60t. It's a vector that rotates in the complex plane in the positive direction. This is a vector that rotates in the complex plane in the negative direction, right? And what I'm saying is the amplitudes of those two guys are always half of this cosine amplitude. So it always takes a positive frequency and a negative frequency to give me a cosine. So no matter what the frequency is, I always have a positive and a negative. So when I'm at DC or at 0, I can't have two frequencies there, right? So it's sort of like there's two terms that are both sitting at 0 that are adding up to give me that 5. That's the way that I think about it, is that it's like there's a 2.5 plus a 2.5, right? If I want to think of it that way. It's like 2.5 e to the j0 plus 2.5 e to the negative j0 are giving me that 5, right? That may not be an easier way to think about it, but in my mind, I think of it as there's always half of the amplitude at the negative and half at the positive, okay? So based on what we have right here, right? 4 over 2 e to the j60, 4 over 2 e to the negative j60. How do I represent that Fourier transform? There's going to be two spikes, right? What frequencies are those spikes going to be at?
Are we starting at the DC? Sorry.
So we already did the DC.
Okay.
So let's say we're talking about this term here.
So then we would go to magnitude of
It'll be 4 over 2.
2.
Yeah, it'd be 4 over 2. And it'd also be, so that would be, this one corresponds to the positive frequency. This one corresponds to the negative frequency, right? So how would I write that over here? How would I draw that? So at the positive frequency, I have an amplitude of 2. And at the negative frequency, I have an amplitude of 2, okay? So this guy here is, the location of this is 2 pi 60. And this guy is located at negative 2 pi 60, like that. Now, what do I do for their angles?
You would have a position of
1 is 60 degree upward, and alpha negative 1 is 60 degree downward.
Yes, that's right. So this guy here would be at 60 degrees up, and this is at 2 pi 60. And then over here, I'd have negative 60 at negative 2 pi 60. Okay, like that. All right. I recognize we're almost at time, but I'm going to go through the other one here. So I've got 6 sine 2 pi 180t. And I'll spot you one here. Let's to keep this simple, let's take 6 sine 2 pi 180t. I'm going to jump that over and say that's 6 cosine 2 pi 180t minus 90 degrees. All right, so I'm just going to give you that. So if I give it to you that way, how would I write that? I'm going to say that's 6 cosine theta. Okay, where theta is equal to 2 pi 180t minus 90 degrees. So if that's the case, how do I write that in complex form?
It would be 6 over 2 e to the j.
Let's just do it this way. 6 over 2 e to the j theta plus 6 over 2 e to the negative j theta. And then I plug in my theta. So this is going to be 6 over 2 e to the minus j90 e to the j 2 pi 180t plus 6 over 2 e to the j90 times e to the negative j 2 pi 180t. All right, all I did was plug in that theta there and then separate out. If I have e to the j times a plus b, say that that's e to the j a times e to the j b, like that, okay? Basically putting all of your math skills to the test there, right? That you've learned at all these different times. So how now do I convert that to the Fourier transform? Well, I've got the two terms. This one, this is my alpha 3. This is my alpha minus 3. Okay? So how do I do that? What do I put on that sketch?
Both would have an upward arrow of 3.
Yep, both have the upward arrow of 3. All right, and they're located at 2 pi 180, so that's somewhere over here. 2 pi 180. And then over here, I'd also have at negative 2 pi 180, the same thing. This guy would have a height of 3. Just be a little bit smaller. Okay. All right, then what would I do about the angle?
At 2 pi 180, it'll be downward arrow of 90 degrees.
Yep. And then
would be, at negative 2 pi 180, it'll be upward arrow of 90.
Yep, you got it. This is 90 degrees. And this will be negative 90 degrees. Okay, at negative 2 pi 180. And this will be at 2 pi 180. Like that. All right. All right. That's how we work through this. In terms of how to use it, I'm not going to talk about that right now. We're out of time. But you should be able to take, this is the kind of thing to get from a waveform to its Fourier transform, you should be able to do. Technically, if you look at it, this guy looks a lot like phasor analysis, right? In fact, it's directly related to phasor analysis as kind of a subset of what we're doing right here. What we're doing is a little bit more general than phasor analysis, all right? So I'm going to stop there.
Will a question like that